Hi all, this is Mr. Yeager for chemistry, looking at gas laws, basically our last unit that we are looking at, and we're going to make this fairly brief. So, with gas laws, we are looking specifically at how gases basically interact and how that affects the measurements related to gases, like pressure, volume, and temperature. And the reason this is so important is we do a lot of analysis when the substance is in a gaseous state, because remember, when it's in a gaseous state, you have isolated every individual molecule. So we are eliminating any of those other possible factors that could affect how the object or substance is reacting. Or even if you have a mixture of substances and you're able to vaporize all of them, each one is its own form, and we can then try to analyze what is in this entire mixture of substances and then go from it that way. Okay? So in this unit, going back to the beginning, sorry, I'm on the second page here, we are going to be looking at what are the gas laws. We're going to analyze each one graphically, and then we're going to calculate them some. Okay? So before we get to the gas laws, I want to talk about the measurements. 3 out of 4 of these we have already used quite a bit this year. I'm starting at the far end with the goofy looking mole cartoon. With the mole, we know what that is. It's the quantity of particles. Temperature. Temperature, we talked about that a lot in the thermo unit. Average kinetic energy of the particles, how quickly are they moving. This has to be measured in Kelvin during this unit. Okay, so we got to be prepared to convert between Celsius and Kelvin. Volume, how much space the object takes up. That's generally in liters and milliliters. The only real new one that we have not played with that much is pressure. Pressure is created by gas particles hitting the sides of the container, and so obviously the more often that is happening, the greater the pressure we have. You know, we can relate it to the idea that it is force applied over an area, but for us it's more about just how often are those particles hitting the sides of the container. There are many, many units of pressure, including atmospheres, millimeters of mercury, torr. Another one we're going to run into is called the Pascal, which is PA. Okay, so there are a lot of different units, or units that we are using. In other years, I might have my students convert between these some. There are conversions between them. I am not worried about that in this particular video this time around. Okay, so what are our gas laws? All right. Our gas laws are basically where we are relating 2 of those variables above, ignoring the mole. The mole is on its own. We'll deal with that in a minute. It shows up in that last gas law called the ideal gas law. But a lot of these we should already have some sort of experience in terms of how one relates to the other. And we just have, you know, each of these scientists came along and did specific experiments to illustrate how one is very clearly related to the other. All right. So again, while we have 3 different measurements, again excluding the mole, we're going to focus on 2 of them while the 3rd stays constant. So the first one we have is Boyle's law. Boyle's law relates volume and pressure at a constant temperature. All right. As you know, if you think about like trying to crush a plastic bottle, when you start crushing it, applying more pressure, what's going to happen to it? It's going to lose volume. So if I increase pressure, I will decrease the space for those gases to move around. When I release that pressure, you sometimes see the bottle again expand back out, because it's able to go ahead, when there's less pressure on it, to kind of increase the volume and space that it has there. So volume and pressure are inversely related. Our formula is simply P1V1 equals P2V2, where 1 is what is the current situation, 2 is what is the new situation when I've manipulated either the pressure or volume. Again, I'll give you 3 out of 4 of those numbers, and you solve for the last one. Charles' law relates temperature and volume at a constant temperature. A good example here is a hot air balloon. The air pressure outside the hot air balloon always stays the same, okay? But if I increase the temperature inside the balloon, what will the balloon start doing? It'll start expanding. So temperature and volume are directly related. Our formula is V1 over T1 equals V2 over T2. So again, when you see where you have the relationship where the 2 variables are over each other, that leads to a direct relationship between those 2 variables if I want the outcome to be the same every single time. Okay? T must be in Kelvin. That's going to be something that kind of permeates throughout all the formulas. Gay-Lussac's law relates pressure and temperature at a constant volume. So therefore, now I'm increasing the temperature, but I'm not allowing the volume to change. So what's that going to do to inside the container? It's going to increase that pressure dramatically. All right. Examples are ones where, and again, I do not recommend this at all. This is very, very dangerous, so don't do it. But an example is where somebody has thrown some sort of compressed container into a fire, and you can see that thing possibly explode in the end. Again, that's a very, very bad idea. Do not do that. But pressure and temperature are directly related, so we have P1 over T1 equals P2 over T2. So, obviously Charles and Gay-Lussac's law are very similar mathematically, all right? So we should see that graphically too when we get to the graphs, while Boyle's law is the opposite of them. It's going to be an inverse relationship. The last one I have here that is very important is this ideal gas law. And this is where we put everything together. We can change multiple factors. Again, Boyle's and Charles and Gay-Lussac's are specific because we have to keep one of those measurements constant. If we don't, the law kind of starts falling apart a little bit. We don't see it work exactly as we expect. The ideal gas law puts that all together and relates it to moles as well. So we can now go how much stuff is in there and how the amount of substance will affect how much is in there. In all of Boyle's, Charles, and Gay-Lussac's law, we're keeping the amount of the gas the same in each situation. Okay? Ideal gas law, we can change it up. So our formula is PV equals nRT. PV equals nRT. N is moles again. We usually use N as moles in our formulas. And then we have this R value. R is the gas constant, and it's 0.0821 atmospheres liters over moles Kelvin. I'm not so worried about you remembering the units. Again, the units for constants are always a way just to cancel out units in the formula to get what we're looking for. But it's going to be 0.0821 atmospheres liters over moles Kelvin. All right? So those are all our formulas. So let's play around for a minute and do a couple of problems. So again, the big thing here is just to read it carefully and go, okay, based on what's given to me, which law am I using? Okay, especially if I'm giving you the laws. So the volume of a gas at 99 kilopascals is 300 milliliters. Kilopascals is pressure, and this is volume. If the pressure is increased to 188, what is the new volume? So you can see what's going on here. We're doing P1V1 equals P2V2, solving for V2. All right, this is Boyle's law. So from there, let's just plug it in, make sure we get it all correct. So 99.0 times 300 equals 188.0. I guess I should put the 0.0 there. Times volume 2. And if you just divide out the 188, 99 times 300 divided by 188, I believe this comes out to something like 158 milliliters. And that would be correct sig figs too, because 99.0 is 3. But there you go. And again, we should go, does this make sense? Does this make sense? The pressure is increasing, so what should the volume do? It should decrease. There's an inverse relationship between pressure and volume. Let's do another one. I'm not going to do necessarily all three laws in this, but you can get the idea of how these work. The pressure in an automobile is 1.88 atm at 25 degrees Celsius. What will be the pressure if the temperature increases to 37 degrees Celsius? So you can see pressure, temperature, pressure, temperature. This is Gay-Lussac's law. Okay. And so this would be P1 over T1 equals P2 over T2. So it would be 1.88, but I need to change Celsius to Kelvin. So 273 plus 25 is 298. That will make a difference in my final answer if you forget to do that. So 1.88 over 298. All right. And then over here we would have 273 plus 37 is 310 over P2. You can look at this as basically cross multiplication if that helps you out. Okay, you can cross multiply the numbers essentially, or you can just divide the numbers on the left and then multiply by 310 on the right. Whatever makes it work for you the best. Okay. I am getting that my pressure, my new pressure is 1 point, I gotta do only 2 sig figs because I have the 37 and stuff. 1 point, actually I'm getting 2.0 ATM. 2.0 ATM, okay? So that is what I have, 2.0 ATM. Does that make sense? Temperature is going up, so pressure must go up as well. All right, let's do an ideal gas law problem so you can see that next with it. With ideal gas law, I might not always give it to you in moles, so be prepared to obviously have to convert grams to moles, but we could still solve for it. So what we can see here is it's asking for the volume. I'm giving you moles. I give you the temperature nicely already in Kelvin, so you don't have to change it. And here's the pressure. So my formula is PV equals nRT. P is equal to 0.900. Solving for volume equals 0.323. That's the moles times 0.0821. That's what R is, times 265. So 0.323 times 0.0821 times 265 divided by 0.9. V is equal to 7.81 liters. Again, I should be finishing up in liters in this particular case. So the volume of this gas will take up a space of 7.81 liters based on the pressure, the temperature, and the amount of particles present. Okay? So that's basically it. Identify which law you need to use, which formula, and then move on from there. So last thing, the gas law graphs. All right, I'm just showing you right here already. You're going to be able to I might give you a graph and go, which of these laws is this one illustrating, or what should the law look like if I make you draw it? All right. As you can see, Boyle's law has an inverse relationship. All right. It's fine where I've even seen this sometimes as a straight line. In the end, it should be a curve. Okay. But it's the idea that we should see as volume go up, pressure should go down. Okay. That's what we're looking at here. This is pressure on this side here. All right. So they're showing the inverse relationship between the two. Charles' law and Gay-Lussac's law, they should have a line going up because as temperature increases, pressure should increase as well. It doesn't matter which unit you have on the axes, we should still see the same thing occur on both sides. All right? But that's basically it. That is everything in this very, very brief little unit about gas laws. And so we are all finished, I believe, right? All right? So that's what we're looking at there. Done, done, done. So thank you very much, and have a good one.